Hello, everyone. I'm Greg Smith, the Curriculum Coordinator for the BioNetwork Bioprocessing Center, and welcome to today's webinar entitled Safe Drinking Water from Source to Tap, Meeting the Challenge for Future Needs. Our panelists today are Jesse Chadwick, chemist, and Julius Patrick, Operations Coordinator. Both are with Greenville Utilities Water Treatment Plant located in Greenville, North Carolina. We'd like you to feel free to ask questions by typing them in the chat box located on the right side of the screen. I'll be keeping a record of each question that is submitted, and we'll have time at the end of the presentation to address all of your questions. Please mark your calendar for our next BioForum entitled Opportunities for North Carolina Farmers and Growers to Produce Higher Value Crops, Part 2. This will be on September 17, 2012 at 10 a.m. Registration for this event is free and is available online at ncbionetwork.org. We would like to remind our audience that if you log on to ncbionetwork.org/IET, you can take advantage of our free interactive e-learning tools that we have created. These cover a wide variety of topics, and we are certain you will find some of these that you can use. Thank you. We're excited to have you all meeting with us, and at this time, I'll turn it over to our panelists, Jesse Chadwick and Julius Patrick, and I believe Julius will be starting.
Good morning. My name is Julius Patrick, and I'm the Operations Coordinator for Greenville Utilities Water Treatment Plant. I'm the backup operator responsible in charge of day-to-day operations, ensuring compliance with the EPA and state drinking water regulations. In today's webinar, I will be discussing different processes and chemicals used at the surface water treatment plant. I will discuss source water, surface water treatment process, which includes coagulation, flocculation, sedimentation, filtration, and disinfection, process control, and operator requirements. So there are two types of source water, either surface waters or groundwater. Large-scale water supplies tends to rely on surface water resources. Small water systems tend to rely on groundwater. In the United States, consumption consists of 35% using groundwater and 65% using source water. Source waters are the waters that you can see from land surface, which are your rivers, lakes, and reservoirs. And groundwater, or water that is underground, usually the groundwater is pumped from wells that are drilled into aquifers. An aquifer is an underground layer of permeable rock, sediment, or soil that yields water. Groundwater typically is requires less treatment than surface water. Drinking water wells may be shallow, which are 50 feet or less, or deep, which may be drilled more than 1,000 feet. And there's a wide range of gallons per minute for your wells also. Some wells produce as little as 150 gallons per minute, while your other wells may produce over 1,000 gallons per minute. And if you look at this right here, this is your column that's drilled down into your aquifer. The water then goes through the series of pipe, and it enters into your treatment process, which right here we have the first door, we had chlorine for disinfection. It goes through a static mixer, which is right here, and then it goes, ammonia is added for monochloramine formation, and then it's entered out into the distribution system. The amount and type of treatment applied by a public water supply varies depending on the source type and quality. Many groundwater systems only uses chlorine, while surface water are exposed to direct weather, runoff, and the atmosphere. Therefore, they're more easily contaminated and requires more treatment. So this webinar will focus mainly on surface water treatment. So how do we get our water from the lakes and rivers to the treatment facility? We have raw water intakes. The main purpose of the intake structure is to draw in water while preventing leaves and other debris from damaging raw pumps or pipes. If you look at your picture right here, we have a screen which can range from 8 to 12 feet long and in diameter from 2 feet to 4 feet, with a 1/4 inch mesh to prevent all your leaves and debris from entering your raw pump station. Then it goes through your pipe, and typically this top picture is one that's under construction, but one that is completed when the water is filled. This is what you see. You don't see the screen from above surface. The water enters into a raw pump station. This pump station has 3 levels, which your top level includes your pumps. This is your second level with your piping, and below this concrete is your wet well, which where the water enters from the river. Then the water is pumped out of your pipe into either directly to the plant or into a pre-sedimentation impoundment. If you have a pre-sedimentation impoundment, it allows the heavier particles to settle out, which reduces the solid removal load at the plant, making the water easier to treat. This results in less chemicals. The impoundment also serves as allows time for bacterial die-off and reduction of turbidity. So what's in surface water to make us have to treat it before human consumption? We have what you call colloidal matter, which is the suspended matter of raw water comprised of very fine and widely dispersed solids. These particles are so small that it's virtually impossible to settle, float, or filter until they have first undergone treatment. They're smaller than 1 millimeter, so you can't see it with your naked eye. It's the major cause of objectionable turbidity, color, and taste in drinking water. The matter remains suspended almost indefinitely due to it having a negative charge. It originates from minerals, which include silt, clay, silica, and metallic salts. Organic, which are your humic and fulvic acids stemming from decompositions of vegetables and animal matter. Or biological, which are your microorganisms, including bacteria, plankton, algae, and virus. Before entering the water treatment process, pretreatment chemicals or mechanical devices are used. First, you have copper sulfate, which can help control taste and odor caused by algae growth. Lakes and reservoirs are susceptible to algae blooms, especially after fall or spring turnovers. Picture on your right is potassium permanganate, or the liquid form is sodium permanganate. It's a strong chemical oxidizer used to destroy many organic compounds and oxidizing iron and manganese in the water. You have to be careful about overfeeding permanganate, because if you overfeed it, it can cause a pink water out in the system. And we've heard some cases in the past the overfeeding causes pink water in the distribution system. Next, you have aerators, which are used to circulate the water to reduce odors and cut down on algae. The picture on your left is called a solar bee, and if you can see the solar panel at your top, it uses solar to generate the paddles to circulate the water. This technology is an example of mechanical mixing of the water body. It employs a floating solar power system with a mixer and an intake hose. Only the top 4 to 6 layer feet can be mixed to break the blue-green algae cycle. The picture on your right is diffuse aeration. The stratification of a lake can be achieved with diffuse aeration. The diffusers are normally flexible tubes that are installed on the bottom of the lake, right here. And right here you have a compressor that's sending compressed air to the bottom of the lake. The air bubbles move upwards, transferring oxygen to the surrounding water while carrying anoxic water upward as well. Once the cold aerated water reaches the upper layer, it sinks back again, bringing oxygen to the bottom level. This action causes later the lake to destratify or turn over. we have powder activated carbon, which is black in color, and is good for tasting, odor, or color removal by absorption. It's also good for TOC reduction. The picture on your right is hydrated lime, or the liquid form is caustic, and is commonly used for pH adjustments. It's used when the natural alkalinity in the raw water is too low to produce complete precipitation of alum. Making the water slightly alkaline ensures the coagulation and flocculation process would work effectively. So here are the steps again for a conventional surface water treatment plant: coagulation, flocculation, sedimentation, filtration, and disinfection. We will discuss each stage step by step, starting with coagulation. Coagulation means to agglomerate or to stick together. Most naturally occurring particles in the water have a negative charge. Coagulation eliminates the colloidal matter, which includes your minerals, biological, and organic matter. The first stage is the stabilization of particles. Basically, its action is to neutralize or reduce electrical charges and promotes the agglomeration of these particles. So what's happening during the coagulation process? The colloidal particles and coagulant chemicals result in their cohesion or sticking together. The coagulants neutralize the negative charges of these very small and widely dispersed colloidal particles surface and produce a spongy mass called insoluble floc. The floc entraps, absorbs particles of minerals, organics, matters, and the microorganisms, which are all part of your colloidal particles. Coagulation and flocculation are important barriers to microbiological contaminants and are very key. If the coagulation process is not properly done, then the remaining process will be affected, resulting in using more chemicals or even wasting water. The best range for coagulation usually falls between the pH of 5 to 7. And here's an example of coagulation. Picture on your left gives you two colloids, which they have a negative charge, which is called electrostatic repulsion. And basically, this is your negative colloids repel other negative charged colloids. The picture on your right is the addition of coagulant. In this case, we're adding aluminum sulfate to neutralize the charge, which make the colloidal particles to become more stable so they can stick together. The common coagulants used in a water treatment plant are aluminum sulfate, which is we know as alum, polyaluminum chloride, or ferric sulfate. Aluminum sulfate is the mostly widely used coagulant. It reacts with alkalinity to form positive ions, which remove contaminants by absorption. The advantages are it's rarely dissolved with water, and it does not cause a slightly reddish-brown staining of your floors, equipment like ferric sulfate does. The disadvantage of alum is that it's only effective at a certain pH range, which is usually between 5.5 and 6.5, and good flocculation may not be possible with alum in some waters. Polyaluminum chloride it has a highly charged species that require little or no alkalinity to precipitate floc. It's very rare to have to feed lime or caustic with polyaluminum chloride. It doesn't suppress the pH like alum or ferric does. Due to your high charge of polyaluminum chloride dose, it may not increase as much during increased contaminant loading, which results in feeding at lower dosage than alum. Ferric sulfate or chloride is an iron-based coagulant effective in reducing biological decomposition products at a low pH. Coagulation is possible with ferric sulfate at pH as low as 4.0. The advantage of ferric is the floc form is heavier than alum floc, which makes it more easier to settle during sedimentation phase. And more plants are using ferric for TOC removal today. You also have coagulant A's to kind of put some weight on the flock to make it easier to settle. They're called organic polymers. You have cationic polymers, which has a positive charge, anionic polymers, which has a negative charge, or non-ionic polymers, which has a neutral charge. The most important consideration in coagulation flocculation process is the selection of the proper type and amount of coagulant chemicals to be added to the water being treated. To your picture on your right, you have a jar tester, which consists of 6 beakers. The operator or the lab personnel fills the beaker up with 1 to 2 liters of raw water. You make up a stock solution, which consists of your alum and caustic. So right here, this is jar 1. Your plant dose, say, we're going to just do an example here. Say your plant dosage was feeding 40 parts of alum and 5 parts of caustic, and you were having water quality issues. So you want to make your middle jar right here at that dosage 40 parts of alum and 5 parts of caustic. So this jar you want to make 6 parts of alum, 3 parts of caustic. This jar 38 parts of alum, 4 parts of caustic. This is your plant dosage right here. This jar right here 42 parts and 6 parts of caustic, 44 parts of alum and 7 parts of caustic. And this jar right here 46 parts of alum and 7 parts of caustic. And what happens is it goes through a mixing at 100 RPMs for a couple of minutes. The mixer slows down and turns at a rate of 15 RPMs or for around 30 minutes. Then it goes through the sedimentation. This relates to the detention times, mixing conditions, and settling conditions. The operator observes flock formation, rate, size, and sedimentation based on different coagulant dosages. The operator collects a turbidity to test the clarity of the water, and also pH, check for pH. If it's done correctly, it's a real valuable tool to help operators to know when they need to go up on the dosage. So say this jar was the best dosage, the operator will adjust the plant dosage to 44 parts and 7 parts of caustic. Next, we'll talk about infrastructure in the plant. Rapid mixers are mixing of chemicals by mechanical mixers into the water in as short a period of time as possible. This only takes several seconds. Flocculation is slowly stirring process that causes the gathering of small coagulant particles into a larger settable particle. The goal is to create a flock of good size, density, and toughness for later removal and sedimentation. Flock formation is controlled by the rate at which collisions occur between particles and by the effectiveness of these collisions. Detention time is very critical in conventional filtration, and it requires up to 30 minutes. After your chemicals have been added into the rapid mixer, the water flows into a series of flocculators. And right here, they're square, so this is 1 flocculator, this is 2, 3, and so on. And each flocculator has a mixer. And below the mixer is a shaft, and it has a propeller, or in other applications, there may be paddles or turbines. But what's happening is the water flows into the flocculators, and it goes through a series of baffles. So it flows on this side over here, then it goes through here and goes through here. That helps the coagulant particles to continue to stick together. So as you walk down the basin or the flocculator, you should see the flock particles that they become larger and larger at each flocculator. Here's a picture of a flock. Right here, when you look down in your flocculators at the water treatment plant, you want to see some separation in between the flock. You want nice, large flock, but you want to see separation or some clarity between them, so that lets you know that the coagulation and flocculation process is working like it should be. You remember earlier I talked about colloidal matter has a negative charge and your coagulant has a positive charge, so your desired is to have a neutral charge. At most plants you have what you call a streaming current monitor, which is a display that lets you know the charges in your treated water. So you want the display to read around 0. If it reads way above 0, that means that you're overfeeding, and the operator would have to decrease their coagulant. Or if it's reading way negative, that means you're underfeeding, so the operator will increase their coagulant. After coagulation flocculation is sedimentation. Sedimentation removes suspended particles or particles that are denser or heavier than water. It reduces the direct load on filters, which increase overall runtime. This is accomplished by decreasing the velocity of the water being treated below the point where it can transport settable suspended materials, allowing gravitational forces to remove particles held in suspension. So basically the flock particle moves to the bottom portion of the basin. Picture on your right is a sedimentation basin. Typically your flocculators, they run in series, but your basins run in parallel. So basically you have the water coming in right here. Right here there's a concrete wall called a sealing wall. The wall has hose to allow the flocking water to flow through uniformly, allowing the flock to settle and the cleaner water to continue to travel the length of the basin. Also, the velocity is greatly reduced at this portion to allow the gravitational forces for the flock to settle. From this point to this point, depending on your flows, it takes about 4 to 5 hours. And if I back up a little bit, from the river, if you have a pre-sedimentation impoundment, it takes about 5 to 6 hours. Your flocculation process is about 45 minutes, and here's about 4.5 hours. So basically from the river or the lake to this point right here, it takes about 5 to 6 days, on average 6 days, and we're still not done with the treatment process yet. The picture on your right is pretty much an example of sedimentation. Your cleaner water is at the top, and your flock particles settle to the bottom, and it turns into sludge. Here's another example of a sedimentation basin. You have your inlet zone. Your water flows through the sealing wall, goes through a settling zone. Your flock it settles to the bottom and goes into your sludge zone, and your outlet zone is your cleaner water, which goes into your next phase. Okay, this is a picture of a sludge collection system. This is called a Heterotrophic system, and it runs this track usually once a day. And what it does, along this manifold, there are holes at the bottom, and when you open the valve, it sucks the sludge from the bottom of the basin through this hose and carries it out back into our waste collection system. Some plants that do not have this have to actually remove the sludge manually, and these sedimentation basins are drained maybe once a month, which continuous units can be only drained twice a year for inspection. This basin right here, it can hold up to 450,000 gallons of water. So think about the water that we're wasting if we don't have the sludge collection system. And also it's very labor intensive. So these units right here is a way of conserving water. Also in the settling zone, you have what you call tube cellars. Water flows up through the slanted tubes or along the slanted plates. Flock settles out in the tubes or plates and drifts back down into the lower portion of the sedimentation basin. So basically you got your water coming up, right here it's flowing up, and because of gravity, the flock's going to settle back down to the bottom of the basin, and your cleaner water is continuing to travel through the next stage. These tube sellers allows the plant to flow more capacity without having to physically build more infrastructure. So basically, if you have tube sellers, you can double the capacity going through your basins. Next, we're talking about the filtration process. And it's the process of passing water through materials such as bed of coal, sand, or other granular substance. Facilities use filtration to remove all particles from the water. Any particles which escape removal in sedimentation basins are removed by filters, which follows the sedimentation process. And there are different types of filters, or gravitational filters, pressure filtration, or slow sand filtration. This is a picture of gravity filter right here. You have your water coming in from the top, and the media consists of 36 inches of anthracite and 12 inches of sand at the bottom with an underdrain system. So any material or particles that didn't settle out in your sedimentation basin is trapped in this media. After 96 hours of runtime, or based on turbidity or loss of head, the filter has to be backwashed. So basically, the flow is reversed. A backwash pump introduces clean water from the bottom of the filter, causing filter media to expand about 50% and allowing the particles to flow over into your waste trough, and it goes out to your waste collection system. And this is done. This is also dictated, like I said, by turbidity, loss of head, or hours on the filter. After leaving the filters, water enters a series of flumes under the floor of the filter pipe gallery. Post-filtration chemicals are added in these flumes. We add fluoride for tooth decay prevention, phosphate for corrosion control of your distribution pipe, caustic or lime for pH adjustment, or chlorine for disinfection. Other chemicals may be added depending upon the water quality. The last stage is disinfection, which is microorganisms are destroyed or deactivated, resulting in termination of growth and reproduction. Disinfectants must have a residual effect, which means that the residual remains active in the water after disinfection. A disinfectant should prevent pathogenic microorganisms from growing in your plumbing after disinfection. Disinfection also can be injected prior to filtration to control the biological growth, remove iron and manganese, remove your taste and odors, control your algae growth, and also color removal. Chemicals or process used for disinfection, which is chlorine. Chlorine in addition to ammonia, which is monochloramine, ozone, or UV. I'm going to talk about each for just a few minutes. Chlorine can come in as gas, which are in cylinders, or liquid, which is sodium hypochlorite. And sodium hypochlorite is delivered at 12.5%, and some plants batch it or add water to dilute it to 6 to 7%. This makes it just a little stronger than your household bleach. Chlorine is widely used because it's relatively inexpensive. And the main objective is to maintain chlorine residuals that will remain in the water as it travels through the distribution system. Ozone is a colorless gas that has odor similar after a major rain, a thunderstorm. It smells like it gets the same smell as after a major thunderstorm. Ozone is more than 50% stronger oxidizer and acts as 3,000 times faster than chlorine. It has greater disinfection effectiveness against bacteria and virus compared to chlorination. The disadvantages: ozone is unstable and it would degrade over time frame ranging from a few seconds to 30 minutes. That's why it must be generated on site. Here's a picture of your ozone generators right here. You have your power supply units, and this is the inside of an ozone generator. And not sure if you can really see, but you have a matrix of wiring that are collected to dielectrics. And what happens is the dielectric, the power supply unit, supplies electricity to the dielectric. You have liquid oxygen that comes in and is converted into dry gas. And what happens is when the oxygen, the O2 molecule enters into the ozone generator, it hits the dielectric. Some of the molecules hit the dielectric. They split into O1 molecules. The O1 molecules become very unstable, so then they attach to an O2 molecule. So you have O1 plus O2 is O3, and we generate ozone. Typically, in your typical treatment, only 10% of your O2 molecules is converted to ozone, and your remainder remains as oxygen. Then once the ozone is generated, it's piped down into a contactor, which either has side stream injection or diffusers to disperse it into the water. UV radiation is another new technology. Unlike most disinfectant, UV radiation does not inactivate microorganisms by chemical interaction. UV radiation inactivates organisms by absorption of the light, which causes a photochemical reaction that alters molecular components essential to cell functions. The genetic material, DNA and RNA, is rearranged and they can no longer reproduce. They are therefore considered dead, and the risk of disease has been eliminated. The advantage of UV is that it's environmentally friendly because you don't have any byproducts, no dangerous chemicals to handle or store, and no problems of overdosing. Here's a picture of a UV reactor that's just manufactured, and this is a picture of one that's actually installed. And what you have here is the UV light source, which is enclosed in a transparent protective sleeve, is mounted so that the water can pass through a flow chamber and UV rays are emitted and absorbed into the stream. UV reactor contains high intensity UV bulbs which shine on the water as it passes through the reactor. Now, next the water enters a clear well or ground storage tanks, which provides storage for treated water before it goes through the distribution. Your tanks can either be below ground, which this one is partially below ground, or above ground. Both these tanks are 3 million gallon tanks each, but there's a wide range of there are some storage tanks that holds as much as 20 million gallons. So it depends on the size utility. This is your finished pump station. Finished water from the clear well or ground storage is pumped into the distribution system for customer usage. So basically, once this motor is turned on, the water goes through this piping and goes through this distribution main, and then it goes out into the customer. The same here. So there's always questions, why are the storage tanks elevated out in the system? Well, they're elevated because, or they're told to provide pressure. A typical municipal water supply runs at between 50 and 100 psi. Each foot of height provides 0.43 pounds per square inch of pressure. And before I got in the water industry, I always thought that this whole entire tank was filled with water, but it's not. This right here is just empty space. Actually, you can actually go inside the tank. From where the bowl starts right here is actually the portion where you have water from here. This tank right here holds 1.5 million gallons, and this is a 3 million gallon tank. An underground network of pipes typically delivers drinking water to the homes and business served by the water system. So who's at the plant making sure that the water flows to the tap is treated properly? All public water systems have a certified operator responsible in charge for each water treatment facility. Each plant must have an operator with at least a C surface certification on the premises at all times that the plant is in operation. Operators monitor the treatment process from start to finish. State-of-the-art plants have SCADA systems to monitor this process. Continuous monitoring analyzers, flow transmitters, pressure gauges, and other components are transmitted back to the central PLC so that operators get feedback 24/7. Operators make chemical adjustments, turn on and off motors, and make decisions based on the information provided by SCADA to ensure that quality, safe, and aesthetically pleasing water is produced daily at the lowest reasonable cost. Most facilities operate 24/7. Plants must be staffed with an operator 365 days a year, with most operators working rotating shifts. Small water treatment plants have one operator, while larger water plants may have 3 to 4 operators per shift. The demand for certified operators are growing as regulations become tighter. For North Carolina, the water treatment certification operators requirements, to obtain a C license entry level, you must have completed an approved school, have 6 months experience before taking the exam. This year, the board has revised the policy to introduce an apprenticeship license. This allows someone interested in the water industry to take a C-level exam once an approved school is attended. Upon passing this exam, a temporary license is issued. Once the applicant or the examinee finds employment, they can be issued a permanent license after 6 months. And that concludes my presentation from the source to the tab. Next, I'll turn it over to Jesse Chadwick. He's the chemist, and he'll be presenting on water quality.
Good morning. As mentioned earlier, my name is Jesse Chadwick. I work in the water quality laboratory. Julius has given you a lot of information in terms of the process of drinking water, in terms of various chemicals and processes that are used. But even though the process is a good process, we still have to find a way of being able to make sure that the water is safe going out to our customers. So this morning, I'd like to give you just a few information in terms of what we do into the lab to make sure that when you receive the water at your home, it's safe. So our agenda will cover some of the things such as sources, microbiological analysis, physical chemical analysis, inorganic compound monitoring, lead and copper monitoring, disinfectant by product monitoring, disinfectant residual monitoring, radiological monitoring, synthetic organic compound monitoring, water organic compound monitoring, some additional monitoring, customer relations, and resources. So as you see, we do a lot in the laboratory. Some of the sources, Jesus made mention earlier in terms of we get our water from rivers, lakes, and deep wells. And deep wells are just, as he said before, just pipes down into the ground that pulls water from underground aquifers that we can have water for our treatment process. Source and finished water samples analyzed for total and fecal coliform daily. Additional samples are collected from the distribution system. Several techniques are used for analyzing drinking water for the presence of total and fecal coliform bacteria. Coliform bacteria are aerobic or facultative anaerobic, gram-negative, non-spore-forming, rod-shaped bacterium. Fecal coliforms are a subgroup of coliform bacteria which are present in the guts of warm-blooded animals. And some coliform examples are E. coli, Shigella, Salmonella, Enterobacter, Serratia, Proteus, Yersinia, and Vibrio. There are several methods that are used to identify total and fecal coliforms. Some methods do not specifically identify the organism. The presence of total and fecal coliform are indicators of potential bacteriological pathogens. The presence of coliform bacteria can trigger a boil water notice. You might have read something in the newspaper or seen something on the news that some systems have instituted a boil water notice. Typically, there's probably a bacterial issue, and that's why they are preventing any issues with soil health by having the customers boil their waters. Some water systems perform their bacteriological analysis in-house, and others send their samples out to commercial laboratories. Labs that perform their analysis in-home or in-house, I should say, must be certified by their state or by EPA. Labs must perform and pass a biannual performance testing to maintain their certification. So the state comes in, reviews what we do in the laboratory, as well as we have to do what we call performance samples to maintain our certification, to make sure that when we're sampling the water that we're sampling it correctly. One of the methods that we use in terms of doing analysis for specifically for total coliform is the membrane filter technique. One of the techniques is the M-indoless, which produces a green metallic sheen, and I'm not sure it shows you very well on this plate right here, but it should, in terms of the M-indoless, gives you a green metallic type colony, let you know that it's an E. coli colony. But this is what we call a presumptive test. It means that there is a potential that there is E. coli or coliform bacteria on it. So what we have to do is what we call a confirmation test, and this is where these tubes are involved. We take a sample bacteria and actually inoculate these tubes, and what we look for is the gas production, as you see here, or in this tube here, fluorescence, to determine if this is an E. coli positive sample. Once again, this is called the presumptive test, and this is called what we call the confirmation test. Now, all medias do not require a confirmation test. Some of those are have listed here for, like, for example, M. coli blue 24. It produces the blue colonies, which is this one right here. You have your M.I. agar. If the E. coli are present, they produce a blue colony, which may not be shown very well clearly. And you also have chrome cult, which is the last one right here, that produces a blue or violet color if E. coli is present. The next procedure is what we call presence and absence. Many systems have moved away from the membrane filter technique because it is very time consuming. As you saw before, it takes the confirmation if you use an M-indoless procedure. If total coliform or fecal coliform organisms are present, the media will change color. And here are some that are listed here. You have, first of all, it's the color, which produces a yellow color, and fluorescence, which is this right here. And you also have what says color sure, which produces a magenta color with fluorescence, which is this examples right here. This is the positive sample. This for what we call total coliform. And if it's a fecal, it's this color right here. And this one here is just a negative sample. So you notice it starts out yellow, it turns purple, and if it's a positive for fecal coliform, it gives you a fluorescence. The next one is the E. coli, which produces a blue-green color with fluorescence, which is this example right here. And you also have, I think, Radiological, which is the other one. It has a similar type situation. It produces a blue-green color with fluorescence. Now, some systems want to quantify the amount of bacteria because these samples right here only give you an example of a positive sample, but does not quantify the bacteria. For systems that want to quantify this, we go to what we call quantitrays. And what the system does is fill a sample of water with the reagents. They incubate and they look for a color change. As you see, these samples cells are yellow. And if they put it onto a black light, it will fluoresce. So when they take these values in terms of number of cells that fluoresce as well as turn color, they can go to a key or sheet and determine how many cells of each, and that will give them the actual quantification of the bacteriological colonies. For our industry, we're all beginning to kind of move in terms of actually trying to identify specifically the type of bacteria. Is it an E. coli? Is it a salmonella? Is it an E. coli, enterobacter? Well, there's two techniques, and this is not all inclusive. We have, first of all, what we call the endotube method. The endotube method allows you to inoculate these various agars that you see here that are striped here. Depending on how they react, you can go to a key once again, and depending on what the reactions are, this will give you a specific determination as far as what bacterial colonies or what bacterial species are involved. But the water systems also evolve in the sense that we're now looking at polymerase chain reaction technique, which actually uses DNA to actually determine the specific organism. So many systems are moving in that direction to give them a little bit more information as to what they're seeing in the distribution system in terms of coliform bacteria. The next one we want to talk about is heterotrophic plate count analysis. Heterotrophic bacteria are defined as bacteria that cannot use carbon dioxide as a carbon source and require some form of organic carbon. These bacteria occur naturally in source water, and they're also a part of the distribution system. Some examples are Flavobacterium, Acinetobacter, Pseudomonas. And typically, these organisms do not pose any type of health effect, but high populations can cause taste and odor issues, or it can create such an amount of growth in the system that it can crowd out some of your optimistic bacteria, which allow them to eventually flourish and cause some issues for you. So typically we want to monitor that to make sure that we don't have a high concentration of heterotrophic plate count. As it says here, non-selective media is used to evaluate all types of bacteria present in the sample, but it also allows you to determine the actual concentration of the bacteria, but once again, it does not specifically identify the bacteria. Some of the techniques that are used in terms of this particular method, in terms of looking at HPC or heterotrophic plate count, is, for one, is the pour method. The pour method allows you to put a small amount of sample on a plate, like so, and then you add a warm media on top of that, and you swirl it around and you mix it, and you incubate it. The next one is the spread. Works the same way, but it's a little bit different. Instead of having the media liquefy in the sample, you actually go ahead and solidify the agar and then put the liquid sample on top of it, and then you spread it across the surface of the media, and once again, you incubate it. The next one is going to be what we call the filtration method, which we saw earlier with the E. coli. It allows you to filter X number of milliliters of water and then place it on a hardened agar, and once you incubate it. All three of these methods can be used using either the standard plate agar or the R2A agar. The standard plate agar typically is used for 48 hours in terms of incubates for 48 hours at 35 degrees C, and the next one is what we call the R2A agar. This agar is incubated at room temperature. Typically, we let it go from 5 to 7 days. Many systems like the R2A because it gives them a more representative number in the distribution system. So a lot of folks are actually going to this particular media in terms of giving a better, you may say, an assessment or an investigation for what's going on in the distribution system in regards to HPCs. The last one here is what we call SimPlate. SimPlate is a little bit different. It is still looking for HPCs, but instead of using counting as such as individual colonies, as you see up here, it allows you to put samples in these wells here, and you let it incubate for 48 hours, and then you can put a black light on it, and depending on which cells fluoresce, you can count these number of wells. You go to a key once again and determine how many fluoresce and don't fluoresce. This will allow you to quantify the number of HPCs in that particular sample. Samples are collected from several points within the treatment process, such as raw, filtered, and finished water. A number of required locations are sampled from within the distribution system. The number of samples are collected is determined by the population of the water system, and let me explain it a little bit. Any water system that has any population, the state requires them to grab so many samples within their distribution system. For example, if a system has 50,000 to 59,000 people, they have to take at least 60 samples per month within their distribution system. If they're from 83 to 96,000, they have to take a total of 90 samples per month within their distribution system. Additional samples can also be taken from our deep wells, as was mentioned before, and also from the aqua storage recovery system when it's in service. When we're collecting the samples, we can collect samples in terms of from our distribution system, either from businesses, they can be schools, they can be individual homes, but utilities have decided to actually put in what we call sampling station. And this is an example of what we're talking about. It's just basically a green box with a spigot inside that allows us to access the sample at any time. Of course, if you go into someone's home or business, if it's closed or there's a dog in the yard, it can prevent you grabbing your sample. So several years ago, the utilities made a decision to install the sample locations, which we have access to at any time we need to grab samples. Additionally, we've also divided up our distributions into 8 zones, which gives us an idea in terms of being able to troubleshoot our system a little bit better by zoning off the areas so we have an idea in terms of what's going on in any particular area. And this is just a map showing you those 8 zones, and you notice they're color-coded to kind of give you an idea in terms of where these locations are in terms of sampling stations throughout our distribution system. Process control analysis are performed by the operation staff every 2 hours. As Julius had mentioned before, there's an operator that's on staff, and he's monitoring the plant. And as a part of that monitoring, they actually grab samples to see how the process is going. They look at pH, alkalinity, turbidity, and chlorine residual. The water card in the lab performs additional tests such as dissolved oxygen, iron, manganese, hardness, phosphate, fluoride, and ammonia. Similar to coliform sampling, each site within the distribution sample is also we collect several physical chemical analyses, such as dissolved oxygen, nitrite, free ammonia, pH, specific inductance. Physical chemical analysis is also performed on our deep wells and the aquifer storage recovery system when it's in service. And let me explain a little bit what that is. What the aquifer storage recovery system is allowing us to pull treated water from our system, which is being produced at our water treatment facility, and actually pumped underground. And this water can be stored for a period of time. When we need to recover that water, let's say if we're in high demand periods, instead of producing all this water from our plant, we can actually pull the water from this system and dump into our distribution system. What we have to do, of course, is also disinfect the water, but the water at that point in time can be used by our customers. This allows us to use the ground as a natural storage tank, in essence, that would have stored water here that we can actually use for future needs. Disinfectant byproducts consist of what we call total trihalomethanes. This encompasses about 5 different groups of compounds. The MCL, or maximum contaminant level, is 0.08. Total helicoacetic acids are another group of disinfectant byproducts. It has a family of 5 different parameters that compose this family. The MCL, or maximum contaminant level, is 0.06. Bromate, which is another compound that is created when we are using ozone, and that limit is 0.01. And chlorite is another parameter that's used when we're using chlorine dioxide. And the disinfectant byproducts are formed whenever these compounds, be it ozone or chlorine dioxide or chlorine or chloramines, react with organic matter. They create what we call these disinfectant byproducts. And these byproducts can cause some cancer-causing issues with our customers. So this is why EPA has established this monitoring process of these particular compounds. And additionally, we have to also monitor our disinfectant residuals. EPA requires all water systems to have a minimal amount of chlorine in their drinking water. But they also establish a limit. For example, chlorine is 4.0 milligrams per liter, chloramines is 4.0, and chlorine dioxide is 0.8. In the process of laboratory, we also have to look at some other parameters within our system. One of those being inorganic compounds, which consist of your heavy metals. There are about 17 parameters that we have to look at, and some of those or examples of some of those are mercury, arsenic, and cadmium. We also do what we call lead and copper monitoring. We're trying to access homes that were built with copper plumbing and lead solder, specifically between the years of 1983 and 1985, and we're looking to make sure that the limit of copper as well as the limit of lead do not exceed the 1.3 for copper and 0.015 for lead, because lead specifically can cause mental development in small children and can also influence high blood pressure in adults. We also look at your radiological compounds, such as radium-226, radium-228, uranium, growth alpha, and growth beta. Synthetic organic compounds, these are your herbicides and your pesticides, and there are 39 of these compounds that we analyze for. We don't do that specifically in our laboratory because we don't have the equipment, so those things are typically farmed out to a commercial laboratory. But some of the examples that we look for are 2,4-D, atrazine, and entrin. Of all the organic compounds, these are your petroleum-based compounds. You think about gasoline, for example. There are 51 of these parameters. 2 examples I've listed here are the benzene and the carbon tetrachloride. Some additional monitoring we will perform. One is asbestos. Some water systems have what they call asbestos cement piping, and because they have that piping, we have to make sure that none of the none of the asbestos is leaching off the pipe. So we have to check periodically to make sure that the samples that we're collecting are still asbestos-free. We also look at an organism by the name of Cryptosporidium, which is a protozoa, and this can cause some very serious health effects if people consume this. We monitor in our water to make sure we do not have this particular organism flowing around. The good thing about Cryptosporidium, if it is present, we have ozone, which is very effective against Cryptosporidium. Additionally, look at the organic carbon in our filtered water, and as we said before, the amount of organic carbon when it reacts with chlorine creates these disinfectant byproducts. So it's important that we can kind of keep this organic compound as low as we can, and that's through the treatment process that you just explained earlier. One of the other things we look at is what we call unregulated contaminants, or UCMR. This is a process that EPA uses periodically throughout the years. They will assess 30 new or upcoming compounds that might be potentially in drinking water, such as Chrome-6, cobalt, testosterone, and they allow or mandate water systems to look for these to see what's there. And if they are there and if of significant quantities, they will actually develop a regulation with an MCL, as we talked about before, so that we can start monitoring these on a more consistent basis. Customer relations. One of the things the lab is involved with is investigating some of your water quality concerns. It can be a brown water concern, it can be a taste and odor concern, it could be milky water. Well, the lab is involved in doing that. So typically, if you have a concern, please call your water plant or your whatever your water system is, and just ask if there's something specific that you've read in the news or you have concern about the taste of your water. They're more than happy to come out and investigate your concern. Also, for all water systems, have to produce what they call a consumer confidence report. This is something that's generated on an annual basis. This allows our customer to show you what is actually detected or has been detected in the previous year's water to kind of give you a snapshot in terms of how, or I should say, what your water quality looks like. And this is an example of the one that we produced. It gives you, for example, the chlorine, the copper, the fluoride, the haloacidic acids, lead. And this is something that we give to our customers to kind of give them an idea in terms of how the water is. And last, I'd like to share with you some resources in the event if you want to look more about what we do in our industry in terms of water quality. You can go to EPA.gov, go to the Drinking Water Hotline, or if you're in North Carolina, the ncwater.org/PWS. I thank you for your attention, and hopefully it's been helpful.
All right. Thank you very much, Julius and Jesse. We have a few questions that have been submitted today, and I'll go through these, and hopefully everybody will be able to stay on the line and get some answers to these questions. Our first question, which sites or organizations would you recommend for a recent graduate to join to network? This person happens to be a chemical tech graduate and would like to network with bachelor's and master's graduates, considering how few chem techs there are in the state. Would either one of you like to address that?
Well, I can start as far as ChemTech. There are three major associations here in North Carolina. The North Carolina Waterworks Operators Association, and these are basically consist of a network of operators between operators, superintendents, and some managers. And the association provides training for operators to get your certification. There are annual schools, and we have annual meetings, business meetings. So that is one that you could join. That's ncwa.com if you're interested in them. North Carolina AWWA also is another association which consists of distribution operators and your engineers, and that you can reach them on websites ncsafewater.org. And the North Carolina Rural Water Association also is another major association which tailors towards your smaller communities. So either one of those associations are a good network for you to consider.
Okay. And Jesse, did you have any you wanted to suggest as well?
Well, I think the ones that Julius has mentioned are the ones that I would also recommend as well.
Okay, great. All right, question 2. How does adverse weather affect your sedimentation basins?
Actually, adverse weather doesn't really affect the sedimentation basins. You know, they're out in the open, as you saw. You may see some, if the wind is blowing a lot, you may see some sloshing of the water back and forth, but it doesn't affect it. The effect comes from your river when, you know, you have a lot of rain and runoff. It affects the raw water quality, but it doesn't actually affect the sedimentation basins.
Okay. Is the water treated or monitored while it is in the final storage tanks?
Yes, it's monitored. Actually, it's monitored through each process. And as far as the monitoring on the storage tanks, we monitor pH. We also monitor chlorine residuals. Those are the two things that the operators monitor. And actually, in the distribution at your elevated tanks, some plants have booster pumps to add more disinfection at the actual tanks.
Okay. And question 4, is water pressure to domestic users from the head pressure of elevated tanks or from additional pumping?
It could be both, but typically here at Greenville Utilities is the pressure from the head of the tank, and the elevation of the tanks here in Greenville Utilities are like 202 elevation. So this pretty much is all come from the head pressure of the elevated tanks.
Okay. Question 5, are there any desalination procedures or desalination facilities used to produce drinking water in North Carolina?
Yes, there is one on the coast, and Jesse may. I have never been there. Do you remember, Jesse?
Kitty Hawk is one that I think there's one at Kitty Hawk, and I think Rodanthe is another one they have on the coast, on the Outer Banks. They are doing some desalination.
Okay, I personally am familiar with the one at Kitty Hawk, so I didn't know that Rodanthe had one too. So, okay. A question was asked, number 6, how deep are the deep wells?
The deep wells here in Greenville Utilities, their hours range from 350 feet to maybe a little 500 feet. But when you go to some regions, they go as low as much as over 1,000 feet. So there's a wide range, and you're trying to pretty much have to drill till you get to the aquifer that has that water source. So it depends on your region that you're in.
Okay. Another question, does the PCR analysis help for risk management and source analysis, and how do you address this, if so?
Well, right now we're not using it for that specific purpose. We're looking at, because we have 2 processes at our facility, one is using ozone and one is using chloramines, and specifically we're trying to identify the specific bacterial type in terms of those that are what we call uses ammonia as a food source and those that uses carbon as a food source, and there are several different bacteria that falls in each one of those sides in terms of what we call nitrifiers versus your non-nitrifiers, and that's our role right now using PCR analysis. So we're not using it for risk management or source analysis at this time.
Okay. We had 2 additional questions submitted just while we've been reviewing these questions, and I'll just read them straight from the chat box. Pharmaceuticals and hormones sometimes can get in the water from humans. Is this tracked and removed from the water system, or is this at the water treatment service?
Well, at this point, they are not tracked, and the reason being is the technologies in terms of the need for various testing procedures to be developed. As you mentioned, as I mentioned earlier, there was a UCMR, and I think I had up the testosterone. That is something that EPA is working on now and trying to develop or put something in place. We have a way of being able to monitor what we call personal care products. But right now, most water systems are not monitoring or having anything in place right now because they're still trying to get up in terms of methodologies, techniques, in order to be able to do it on a more consistent basis.
Right. Are pharmaceutical companies treating their water before it leaves their plant?
They have what they call a pre-treatment program, which our utilities are involved in. So that is being monitored on their end to determine what kind of discharges that they are involved with. And some treatment is involved to some degree. But since I'm on the water end, on the wastewater end, I can't really tell you all of what they're doing. But I know that they have a monitoring program called the pre-treatment program that actually monitors those discharges.
Okay. And our last question today, at what rate are we taking water out of the aquifers compared to the rate at which they are being naturally replenished, and how much has paving and construction significantly affected the rate of replenishment?
I think I answered that one. Right here, there's something called the coastal capacity reduction area that consists of, in North Carolina, there are 15 regions that has for years been withdrawing water out of the aquifers, and so they've been kind of losing ground in aquifers. So the state has mandated that in 2008 they reduced their withdrawal rates by 25%, by 2013 by 50%, and by 2018 it's 75%. Well, these smaller communities, they have to find other sources to serve water to their communities. So you're seeing a lot down in Kinston, the Neuse Regional Water Sewer Authority. They built a plant to serve like Aden, Grifton, and surrounding areas. As far as Greenville utilities, we're supplying water to Winterville, Farmville, Greene County, soon be Bethel. So you have to find other sources. But since the state has mandated that reduction, we'll have seen the water levels in our aquifers come back up to levels back in 1983. So I think, with the continuous monitoring wells throughout the state, I think we're going in the right direction with that.
Okay. All right. We appreciate, there's been a couple additional questions added, but we are out of time, unfortunately. I will take those questions that have been submitted and get those participants some answers to those questions. If you can bear with me for another day or two, I will get you those answers for those who have submitted. You can find out about other BioForum events by visiting our website at ncbionetwork.org. Please mark your calendar for our next BioForum opportunities for North Carolina farmers and growers to produce higher value crops. This is part 2 in a series. That will be presented on September 17, 2012 at 10 a.m. Registration for this event is free and available online at ncbionetwork.org, so please check back soon. I would like to thank our panelists, Julius Patrick and Jesse Chadwick from Greenville Utilities Corporation, once again for today's presentation. And thanks to you for your time, audience, and your participation. This concludes our webinar today. On behalf of all of us at the North Carolina BioNetwork, thank you and have a great day.